take a video of this, of you guys taking a video.
Then you get over, make sure this is going through there.
Okay.
Just shoot the screen the whole time.
Okay.
I don't want anything else.
All right, so this is okay. So this is I'm being videoed here, and then the video of the video, and this is the video of the video of the video.
Go back there.
Mostly humans, is in the high bay and the mid bay right now.
Okay.
So I feel like I got here maybe at about the most exciting peak of insanity.
It's definitely a very exciting time because we are in a kind of a final push to complete the launch system, stage 0 essentially, and it's worth saying that the launch system, the tower, and the chopstick arms to catch the rocket are as complex as either of the stages.
Really?
So, yeah, absolutely, if not more. Like we could produce boosters and ships way easier than we could make the launch site. So therefore, I'd say it is harder certainly than any single booster or ship. Yeah.
Well, I think that's one of those things people don't even realize is the manufacturing out here. That's kind of one of those things that you harp on so much is how that's so important, and that's in the long scheme the hardest part of all this is just the manufacturing.
Generally, manufacturing is underrated and design is overrated. So people generally think that this eureka moment of like you come up with this idea and that's it. Now it's good, but the design, like there's literally 1,000%, maybe 10,000% more work that goes into the production system than the thing itself. So say like how much effort have we put into say designing Raptor versus designing the manufacturing system? It's 10 to 100 times more effort to design the manufacturing system than the engine.
Even of a Raptor?
Oh yeah, absolutely, especially with Raptor. All of our, basically, the amount of effort that goes into the design rounds down to 0.
Right.
Relative to the amount of effort that goes into the manufacturing system. Yeah. And if this was not true, great, I'd like 1,000 Raptors, please. Oh, you can't make them? Oh, okay.
Right.
This is like just very fundamentally underappreciated. If people have not been in manufacturing, especially manufacturing of something that's relatively new, then they don't understand, and they think the design is the hard part, and they think production is like a copier or something like that.
Right.
This is completely false.
Well, it's definitely not as sexy as the end thing. Like, the end product is very sexy, and that's what draws people's attention. But the whole back end of it is what makes it possible.
I can't emphasize enough. I'm trying to correct the misperception that design is the hard part. It is not the hard part. There have been lots of great rocket engines designed. You've spent a lot of time looking at the Russian rocket engine designs. There's some amazing Russian rocket engine designs. They've been doing staged combustion for a long time, and have done, I don't know, hundreds of different designs, literally. So the hard part is not can you design a staged combustion rocket engine. This has been done.
Yeah.
Now, admittedly, ours is higher pressure than before, and it is a full flow staged combustion. But that's a relatively minor increment relative to what the Russians have already done.
Right.
What is super hard about Raptor is how do we make a Raptor where the cost per ton of thrust is under $1,000? Yeah, I mean, we definitely don't want to. The fundamental thing that needs to be fixed is the cost per ton to orbit.
Yeah.
So things that address the cost per ton to orbit are good. Like, humanity will be a multi-planet species if we get cost per ton to orbit to the point where we can afford to become a spacefaring civilization and a multi-planet species.
Right.
So this is, at its heart, it is fundamentally an optimization of cost per ton to orbit and then ultimately cost per ton to the surface of Mars.
Right. Well, and if you're working on getting the cost, even when you're starting to think of it as dollar per ton of thrust, I mean, I don't know if anyone's ever considered that as a key metric.
Yeah.
That's a new thing that I've never thought about, never considered. Raptor is kind of unique because now you're starting to also think about the, instead of thrust to weight ratio, when you have a fixed diameter and a fixed circle area, you're also worried about the nozzle exit to thrust ratio as being a pretty strong consideration too.
Yeah, you basically end up filling up all the area under the rocket. So with this version, we have 29 engines. Sure, there's a lot of beeping.
Yeah.
I'm not sure having this many things beep is actually helpful.
Right. Sensory overload.
Yeah, it's like everything around you is crying wolf.
If everything's in danger,
You just got to tune it out. Yeah, exactly. So it's pretty silly, but.
So this is the nose of booster 4.
Yeah, this is basically, that's the interstage and the fuel tank of booster 4.
Wow.
So, yeah.
What are the little? So obviously those are where the grid fins go, right?
Yeah.
And then what's the thing in between them?
That's actually the mount point. So there are two. It's debatable whether this is the right design or not. In fact, it's like all designs are wrong, just a matter of how wrong. But that's one of the load points for picking up the booster. So that thing that you see, it's this like tiny little. It looks small.
Yeah, it looks like a.
But it's actually not that small at close up. This thing's just high in the air. Like all your sense of perspective is wrong.
Yeah.
And when this lands, it has like basically the density of a beer can.
Right.
You know, an empty beer can.
Right. What is the dry mass?
With like some mass, in the engines, obviously.
What is the dry mass? Are you under 200 tons for booster?
We should be under 200 tons. The mass is a moving target, so you also have to say like, what are your propellant residuals when you land? That's a big deal. Like both how much margin will you have and what's your unusable propellant. Like you can't just go to zero margin, you know, because the thing's going to crater.
Yeah.
So it should be under 200 tons though. So, but as a rough rule of thumb, like the engines, including mounting mass, are roughly 2 tons. So you've got 29 engines at 58 tons. Then the sort of the fuel tank itself and the oxygen tank is probably on the order of well, it's a little heavy right now, so maybe it's like 80 tons or so. Then you got the inner stage where you've got the grid fins, batteries, and a bunch of other things.
Yep.
So that's I don't know, maybe around 20 tons, and then you got propellant residuals, which might be on the order of 20 tons too.
Okay.
So all that should come to, I don't know, call it 160 to 200 tons, depending on the sort of final mass numbers. But like right now, everything's too heavy. Like avionics too heavy. The
avionics even?
Yeah.
I thought just a little.
I mean, it should be, but the grid fins are electrically powered, so we have batteries that are energy optimized instead of power optimized. So, like this grid fence only needs to work for like 2 or 3 minutes.
Right.
So it's very different from like an electric car, which you want to have several hours of driving. So these really we need power optimized batteries, not energy optimized batteries. This is just a short-term thing.
Right.
So the battery mass can probably drop by maybe a factor of 10.
Right.
So that's just one example.
Should we back up a little bit so it's a little... Yeah.
Less clanging?
Yeah. And everyone trying to get their cranes in here and do work. You got a lot of people on set right now.
Yeah, I mean, just like that residuals number is a super big deal on the mass, though. Because the booster is designed to have 3,600 tons of propellant, which is an almost 80% oxygen, liquid oxygen by mass.
Yeah.
Like 78%.
Did you burn at what? Is it 3.5
3.5, 3.7.
Okay. Yeah.
Wow. So, and you want to bias it in favor of oxygen because oxygen is denser and cheaper.
Right.
So, in terms of improving your payload and reducing cost per ton, oxygen is is basically plants make it for free, and plankton.
Yeah.
So it's basically like electricity cost of separation and distillation.
Right. Now,
So
remind me though, is it like, as far as the ratio goes, fuel OF ratio, having the lighter molecule, don't you kind of want that to be spewing out faster or something because it's less reaction? You can accelerate it quicker. Or
yeah, there's a trade-off between. Well, I mean, what you tend to get limited by is you don't want to go too close to stoichiometric because the heat's too. You basically melt your engine.
Yeah.
So that tends to limit you on the OF on trying to go to higher OF.
Right.
That's the actual thing limiting you. You tend to hit the stoichiometric melting point before you roll over on ISP.
Okay.
Generally.
Okay. That makes sense.
Yeah.
And remind me, are the grid fins, do they still fold in?
No.
No. Is that going to be permanently that way?
Yeah. So the what I'm trying to have us all just implement rigorously is the sort of 5-step process. First, make your requirements less dumb. Your requirements are definitely dumb. Does not matter who gave them to you. It's particularly dangerous if a smart person gave you the requirements because you might not question them enough.
Yeah, you might take it as like gospel, like
Yes.
I have to do this thing.
Everyone's wrong, no matter who you are. Everyone's wrong some of the time. So make your requirements less dumb. Then try very hard to delete the part or process. This is actually very important. If you're not occasionally adding things back in, you are not deleting enough.
Right.
The bias tends to be very strongly towards let's add this part or process step in case we need it. But you can basically make in case arguments for so many things. And for a rocket that is trying to achieve trying to be the first fully reusable rocket, there's never been a fully reusable rocket. People don't understand. Like this is like the holy grail of rocketry.
100%.
Okay, and so you really need, you have to run at tight margins because if you don't run tight margins, you're going to get nothing to orbit.
Right.
So you got to delete the part or process step, super important, and you can't like hedge your bets. So that's why the grid fins, for example, do not fold down because that's a whole extra mechanism that we don't need.
And you can just compensate for it by having strong enough engine authority to steer it in the lower atmosphere.
Actually, our simulations so we don't really need any extra engine authority. As long as the grid fins, basically follow the flow, they're not really disturbing the flow. It's really neither here nor there.
So
as long as they don't have a high angle of attack, it doesn't matter.
A few degrees or something, or within a degree or two.
So, but in any case, it's a thing we could add later.
Right.
So now these grid fins are humongous. We'll go see them, but they're like, like a dinosaur bear trap. Okay, it's like a bit of bear trap or a dinosaur. That's what these things look like. And if you have a whole mechanism for folding them, that's like clearly a part that we don't need.
Yep.
So this was a good design decision. That actually I didn't come up with, and it was like great, but it followed the principle of like delete the part, delete the process. And I was like, great, good idea. Let's not fold them. Why were we folding them anyway? Somewhere random, and also if whatever requirement or constraint you have, it must come with a name, not a department, because you can't ask the department. You have to ask a person, and that person who's putting forward the requirement or constraint must agree that they must take responsibility for that requirement. Otherwise, you can have a requirement that basically an intern 2 years ago randomly came up with off the cuff, and they're not even at the company anymore.
Right.
But it came from the, let's say, aero loads department. They're like, actually, no one in the aero loads department actually currently agrees with that. This is by the way happened several times.
So again, it can be literally.
I don't want to put it on the aero loads department, but there's like there's every department. So
it can be thought of as gospel again, but it might be something that's just totally in passing. Like or someone played too much Kerbal and had fins at the top of the rocket, and then it just it did this.
These things are often just way more silly than you'd think.
Yeah.
Anyway, so step one, making requirements list dumb. Step 2, delete the part or process step. If you're not deleting a part or process step at least 10% of the time, basically, if you're not adding things back in 10% of the time, you're clearly not deleting enough.
Right.
And then only the third step is simplify or optimize. The third step, not the first step. The reason it's the third step is because it's very common. It's possibly the most common error of a smart engineer is to optimize a thing that should not exist.
Right.
Okay.
Right.
And you say, well, why would people do that? Well, everyone's been trained in high school and college that you got to answer the question, convergent logic.
Yep.
So you can't tell the professor your question is dumb, that you'll get a bad grade. You have to answer the question.
Yep.
So everyone's basically, without knowing it, they got like mental straitjacket on. That is, they'll work on optimizing the thing that should simply not exist.
Right. Right.
I'll give you an example from way back in the day of Falcon 1. So in the original sort of like when Tom Mueller and I were like batting around, like, okay, what should this rocket look like? I think I was literally in like Tom's kitchen or something, and we had like the spreadsheet and like, okay, we need to like make a minimally viable rocket, like half a ton or whatever, it's something like that, and then initially the spreadsheet had we had an NTO MMH upper stage, so sort of hypergoal upper stage, kind of like a variant of the TRW LIMD.
Yep.
So.
Which I think Tom worked on, right?
Yeah, Tom, the people who trained Tom worked on it. He's not that old.
Yeah, that's right.
It was like a baby, you know.
Yeah.
They were very advanced baby.
He designed it. You know.
But his mentors did work on LIMD. So, Lunar Module Sen Engine. So, basically a pintle injector.
That's right, because that's where the pintle injector comes in, right?
Because you can also deep throttle it and everything. So now the problem with that is how much does NTO MMH cost? It's super expensive. Okay, yeah. It's like a rare chemical. So even if you're like, if Edison and Tesla had a baby and that baby was smarter than both of them combined and said your job is to optimize an NTO MMH upper stage, you're screwed. Okay. So, like nitrogen tetroxide and monomethyl hydrazine are super expensive, and they're also toxic.
They're super nasty, yeah.
Yeah,
just the handling costs alone are probably pretty appreciable.
I think like safety is overcorrected on the NTO-MMH. It went from like nobody had any protection and breathed the fumes all day to it's cyanide. Okay, yeah. and neither of those are true. It's not cyanide. You won't die. And Bill Gusmeyer told me like a story of like when he started at NASA, they actually I think passed around like a cup of like hydrazine so that everyone knew what hydrazine smelled like. So like because it's like a rotten egg smell or something like that. So it literally an open cup of hydrazine, and like obviously he's still alive. So so that's an example of like don't optimize the thing that shouldn't exist. We should not have NTO MMH upper stage.
Right.
Now Dragon does have that, but that's because Dragon's got to do a lot of like nuanced firings of the Draco engines, with very short pulse durations, and if you have trying to have something that's not hypergolic is very difficult, and it can be done. Like, but if you say not hypergolic and not cryogenic, now your options tend to suck.
Yeah.
So, then you start going down the peroxide, barking up the peroxide tree or something like that, and that's or super esoteric monoprops.
Right.
And that's like again back to big money. So.
Yeah. That's step 3.
So, exactly. So getting through these is quite laborious. Sorry for the laborious explanation here, but and then finally you get to step 4, which is accelerate cycle time. You're moving too slowly, go faster. But don't go faster until you have worked on the other 3 things first.
Gotcha.
Like if you're digging, your grave, don't dig it faster. Stop digging your grave.
Right.
But you can always make things go faster. And then the final step is automate. Now I personally made the mistake of going backwards on all 5 steps, multiple times. So I have to repeat this. Yes, multiple times on Model 3, where literally I automated, accelerated, simplified, and then deleted. Like one example I've talked about before is like there were these like fiberglass mats on top of the Model 3 battery pack that were in between the floor pan and the battery. And it was at one point choking the battery pack production line, and I was like basically living on the battery pack production line, like trying to fix the line, because it was like choking the entire Model 3 production program. So the first mistake was we should not have. I like try to fix the automation, like make the robot better, make it like the robot move faster, a shorter path. Increase the torque, delete the reverse 720 degrees on the bolt, because that's unnecessary. Just go forward fast, not at 20% rate, at 100% rate. And instead of spackling glue on the entire battery pack, just put little dabs of glue, because the fiberglass mats are sandwiched between the battery pack and the floor pan anyway, so all you need is like something to hold it in place until you bolt the battery pack into the car.
Gotcha.
So automating was a mistake. Then accelerating was a mistake, then optimizing was a mistake, and finally I said, what the hell are these mats for? And I asked the battery safety team, because I like, are these mats for, what are these mats for? They said, oh, these mats, I said, are they for fire protection or something? They said, no, they're for noise and vibration. So you don't get, and I said, but you're the battery department. Then I asked an NBA, noise vibration harshness team, what's it for? They said, fire safety. So literally, it was like being in a Dilbert cartoon, okay? It was like, actually, I feel like I'm in a Dilbert cartoon quite frequently. So I'm like, are we in some simulation where I'm like trapped in some like Kafkaesque / Dilbert cartoon situation? But that's what it feels like a lot. So then finally, okay, great. Let's try a car with the fiberglass mats and without. And they put a microphone in both, and see if you can tell the difference. You cannot. You cannot tell. In fact, I was like, which one is which? So we just deleted them and just bypassed this $2 million robot cell. It was just a complete pile of nonsense. Another mistake that tends to happen in production is too much in-process testing. When you're first setting up a production line, you don't know where things are breaking. You don't know where things are breaking, so you'll test like work in process at various steps, and because you want to isolate where's the mistake occurring. So a very common issue with production lines is to have is to not remove the in-process testing after you've diagnosed where the problems are. So basically, if you have like a very high acceptance, if things are getting to end-of-line testing and are passing, then you don't need to do in-process testing. So, but what tends to happen is there'll be an initial development engineering team that will be basically debugging the production line, but then they will forget to take out the in-process testing steps. So then what happens is the in-process tester will often choke the cycle time, choke the line production time. It'll be like the limiter. It'll also have some number of false positives and false negatives. But I mean, but like false positives, then you're rejecting good parts.
Right.
Really in volume production, if things are working well, you're really just taking a risk. Will this part will this subsystem be rejected during the production process or at the end? And so you just really want to move things pretty much almost always to just test at the end of the line, and that's it. Maybe there's one or two in-process steps that are hard to test at the end of line, but basically remove almost everything. There was another thing with the battery pack where this is so crazy. One of the things the battery pack has to do is resist water ingress. so it has to be leak proof. So if you drive through deep water, water doesn't come into the battery pack and short out the battery pack. You might have seen some of the videos of like people driving Teslas in like extremely flooded waters,
Just like
where it's
this
like
week, China.
like
Have you
half
seen those
underwater.
ones?
Yeah, people like geez, there was literally a guy, I believe in Kazakhstan, literally drove a Model S through a submerged water tunnel, like it was, and all the other cars were out, and he basically steered the car with the wheels and used the wheel rotation to like a boat and drove out the tunnel. This is important to have the battery pack resist water ingress. But then instead of us doing a pressure test on the battery pack, we're actually pressurizing the inside of the battery pack, which was the wrong direction. And the battery pack lid was glued, was basically had resin that was not cured, and so we were just blurting out the resin, which doesn't make any damn sense.
Right.
Because you should actually be drawing a vacuum on the pack, and not pressurizing it.
Right.
And especially not pressurizing it when there's uncured resin is what's holding down the battery pack.
Yep.
So the pack was failing quite often on the pressurization test, which should have been a vacuum test. Anyway.
Speaking of Gridfin,